Okay, so again, for the people that just came in, I hope you had a great break. I will give you the tests back for keeps on Wednesday, but throw them in the folder once you've had a chance to look at them today. So just a reminder, it's been a while, but last class, which was like a week and a half ago, we talked about the Pythagorean theorem, and we talked about some laws of exponents, and there was a chart with 5 rules in it applying to exponents. Today we talk about integer exponents, and in particular negative exponents is the heart of today's lesson. And I will just put out this reminder that I've taught this course before, and this exponent section is generally very tricky for a lot of folks. Not all folks, but a lot of folks. So just try to pay close attention to all of these different rules that we're going to be looking at, and make sure you're clear not just on how to use them, but when to use them, and just as importantly, when not to use them, because they're really picky about like when they can be applied. So we're going to jump to page 5, which actually was part of the last lesson, but there's something on page 5 we didn't do yet, and that's where we start today. So first thing, do you guys remember we talked about this a to the 0 business? Yeah. Yes, you can. So this any number to the 0 business, you guys remember? What did we define any number to the 0? We defined it to be 1. 1. Okay, so let's come on back here. So 3 to the 0 is defined to be 1. Any number to the 0 is just plain 1. It's weird that it isn't 0, but we talked about why 1 is a good definition for any number to the 0 last time. But what we're after today is to try to give meaning to a negative exponent. So let's take a look at the stuff that I had written last time. So here we are. Just grab one from that pile right there. What does 3 to the 5th mean? Easy question. 3 times 3 times 3, 5 of them, right? Okay. What does 3 to the 1st mean? Just a single one copy of the 3. We looked at 3 to the 0. It seemed like 0 was a good answer, but we decided that any number to the 0 is 1. But what we're after now is to try to give meaning to like 3 to the negative 2nd power. That's what I want to know what it's equal to. You can type it in your calculator. You'll get a number. There are some reasonable numbers that we could just throw out here for how we could define 3 to the negative 2. But there's only one right answer. So I want to get us to that right answer. Whether you know what the right answer is at this moment or not, doesn't matter. Let's just see if we can figure out what the right answer should be by looking at a pattern. Let's take a look at this column of numbers over here. Okay, so we've already decided that any number to the 0 is 1. So that's 3 to the 0 is 1. And 3 to the 1st power is 3. And 3 to the 2nd is 9. 3 cubed is 27. 3 to the 4th is 81. Nothing new there. How do we get from one number to the next in this column? What's the standard rule that gets us up that chart? Just times 3, right? Every number times 3 gets you the one up above, which makes perfect sense because these are just saying stick on another 3. We just have lots of powers of 3's here. So if multiply by 3 gets us up the ladder, then what's the rule that gets us down the ladder? Divide by what? Divide by 3. Everyone agree? Makes sense. So divide by 3 each time to get the number right below. So if we're going to try to give meaning, so we've got all these powers of 3 here. 3 to the negative 1 is the next reasonable power in this list. If we're going to give meaning to it, well, mathematicians really like patterns, and so I'm just going to go ahead and follow the bouncing ball and say, well, let's keep dividing by 3. Chris? Yeah, isn't that perfectly reasonable? Right? That 3 to the 0 has got to be 1 if we're gonna allow this pattern to continue. Great. So let's push past 0 and into the negative numbers here. So we're saying divide by 3 every time. So 1 divided by 3 is just 1/3. That's the next one. And that was so much fun. Let's do it again. We're going to divide by 3 here. Okay, now it gets a little bit trickier because we have fractions getting divided. But how much is 1/3 divided by another 3? I mean, it's written there. Do we buy that it's 1/9? You're taking 1/3 and you're dividing by 3. I mean, if you need to see details, it's not hard. 1/3 divided by 3 is the same as 1/3 times. Remember, division changes to multiplication, and then you flip over the second guy. So it's that, right? Division becomes multiplication and then flip. And then how much is 1/3 times 1/3? Is 1/9. So that's the next guy. And then we can go 2 more steps. We divide by another 3, and 1/9 becomes 1/27. And we divide by another 3, and we get 1/81. And then we start to recognize, well, wait a minute here. 1/9 is really the same as 1/3 squared, right? And that 27 down there is just 3 cubed. And that 81 is 3 to the 4th power. And so we get this rule that 3 to the negative 4 is really 1 divided by 3 to the positive 4. That's what that equation says, right? And that's basically our definition of negative exponents. It's written right up here. If you have x raised to the negative n, we just say, oh, it's the same as 1 over x raised to the positive n. That's all that that says, okay? All right, so that's good. Let me just remind you, I'll give you 2 ways to think about this rule, 2 ways to try to help you remember this rule. If you took Math 095 with either me or Sandy last semester, raise your hand. I just want to get a sense of how many people I'm talking to. Oh, not very many at all. Okay, so then we'll say this to the folks who haven't seen it, which is most of you. Suppose that we have the number 4 to the negative 2. I'm going to put this 4 over, I just put it over 1, so it looks like a fraction. And then I'll look at something similar like 1 divided by 5 to the negative 7th power. And we'll do one more example. We'll say 2/3 to the negative, 8th power. So we're going to figure out what each of these things is by thinking about a kind of silly scenario involving a baby. And so generally babies are either crawling around on the floor or up in somebody's arms. Those are 2 places where you'll find babies pretty often. And so what we're going to say is that if the number, this 4, is up in the top of the fraction, that's the baby being held in your arms, right, up above the floor. The floor is the denominator of the fraction, right? So in the first example, where's the baby? It's up in your arms. Second example, on the floor. Third example, there's actually 2 babies. The 2 is where? It is in the arms, and the 3 is on the floor. That's silly, but stay with me here. Okay, and that negative exponent, we're going to think of the word negative and think, okay, the baby is negative, meaning unhappy. And so if a baby's unhappy, generally you can try to help them by putting them somewhere else. So the baby that is unhappy up in your arms, where does that baby want to be? Wants to be on the floor. So we'll put the baby on the floor. So this is equal to, so I'm going to make my fraction line. I'm going to put the baby on the floor. And by putting the baby on the floor, I'm making the baby happy, positive. So the exponent is now positive 2, not the negative 2 that we had before. And I need a placeholder up here. What's the number that is the placeholder? Is a 1, right? It's not a 0. There's an invisible 1 everywhere. So put it if you need it. And that's our definition of negative exponents, right? 4 to the negative 2 really means 1 over 4 to the positive 2. Okay, the same baby thing works with this next example. Again, where's the baby? On the floor. Baby's unhappy being on the floor. He wants to be picked up. So we pick the baby up. And what happens to the baby when you pick him up? It becomes positive. Positive 7. Placeholder doesn't really matter down there. Okay, this one, twins. The 2 is in your arms. 3 is on the floor. They're both unhappy. How do we make them both happy? We swap them, right? We pick the 3 up, put the 2 on the floor. They're both positive. Okay. So this is something that I got from Sandy, my colleague, and it's something that she got from one of her former students who just came up with this analogy, and Sandy's been using it ever since. All right, so there's the baby way of thinking about things. And if we jump ahead to page, I think it's 9, right here. And at the bottom of page 9, there's just kind of another way of thinking about negative exponents. Let's go to Dan. Dan, can you read number 3, please? Good. So negative exponents, you can think of babies if you like. You can think of this if you like. Negative exponents mean motion. You move the thing to wherever it isn't and make it positive. Okay, there's a whole collection of things here. You're going to do most of them, but I just want to do a couple of them together to get us started. Let's start by looking at part E, right here. 2x to the negative 3. Okay, negative exponents almost always end up with fractions, so I'm just going to put a fraction line to get me started. Okay, that x to the negative 3 is negative. Negative to me means motion, or it's a baby that wants to be put down. So where do we put that x? In the bottom. And what happens to the exponent? It becomes positive. So it's an x cubed downstairs. Now don't write this down because it's wrong, but it's really tempting to say, okay, negative exponents, you put things downstairs. But that negative exponent is not touching the 2, right? The 2 is not affected by the negative exponent. You might need to put a little dot in there to remind you that it's multiplication, and we know exponents come first in terms of the order of operations. So that multiplication comes after you've dealt with the exponent. The negative does not apply to the 2. So where is the 2? It's on the top. It has no reason to move. And that's why I wanted to do this example, just to show you that the only things that move are those things with negative exponents. Kieran? That's our answer. And the goal for all of these here is to get it so you have no negative exponents. That's what we're after, no negatives. Okay, let's take a look at part I. All right, we're going to do this one in a couple of different ways. First thing we're going to do, okay, I see an x cubed. I'm just going to copy it. It's already positive. But then I see an x to the negative 4, and I'm going to deal with that negative. I'll write my fraction line. What is x to the negative 4 the same as? 1 over x positive 4. If you put a fraction, you have to put 1. The x cubed is upstairs, so if you just had that up there, you wouldn't need to put a 1. You could do that, yes, absolutely. Okay, so this is fine, and now we're going to cancel some of these x's. So how many x's are left over, and where are they? There's a single x left where? On the bottom, because there's more of them down there. So there's a single x left over. Those 3 x's cancel with 3 of the 4 that we have on the bottom, and still that placeholder of 1 on the top. So 1 over x is done. No negative exponents. 4. I'm just going to recopy the original. We had a collection of 5 laws of exponents that we looked at a week and a half ago. One of them applied to exactly this scenario here. Does anybody remember what we do with those powers when a problem looks just like this? Is we add them. That's what it said. It was the very first property in that table. You add the exponents. So let's add the exponents. So we have a single x down here. You add the exponents. So I'll put it on the side. 3 plus negative 4 is negative 1. So it's just x to the negative 1. And now we'll get rid of this negative exponent. X to the negative 1 is the same as 1 over x. I'm going to put positive 1 down there just so we see that the negative exponent became positive, but then I would ask you not to ever write a final answer with an exponent of 1. Questions on that one? Okay, both methods are fine. They both get to the same answer. Personally, my preference is to apply those laws of exponents first and then deal with negative exponents at the end. I generally think that's shorter and less prone to error. So I'll say it again. I try to apply familiar laws of exponents first and then handle the negative exponents at the end. So I wouldn't do the first way. I would do it the second way. Okay, let's take a look at 2 more. We're going to go to J right here. Okay, equals. All right, I'm going to start by doing it again the way that I wouldn't do it. Let's just deal with the negative exponents first because it's a new thing for us. So we're going to practice with it. So I have a c to the negative 4. where does that go? In the bottom, and becomes c to the positive 4. And then I have c to the negative 8. Where does that go? On top, c to the 8. Where does that 4 in the front go? On top. It has no reason to move. Again, it's really tempting to just move the whole top to the bottom. That's not right. The 8 down there, again, has no reason to move. So this is our reduced thing, our simplified thing, and now we have to reduce it. Okay, so let's reduce it. What's the familiar property of exponents here? Subtract. Right? When we see this, we subtract. So when we subtract, we get c to the, and then we'll put a little note here, this is 8 minus 4. So upstairs we have c to the 4. And then let's go ahead and reduce the 4 and the 8 that were in the front. 1 over 2. I'll just write the 2. Questions on that? Okay, here's another option. The one that we're about to do is my preferred option, but again, there are a lot of different ways to do these correctly, and as long as you do it correctly, you'll get full credit. I'm just going to copy the original one here. Okay, again, just focusing on this piece right here. What was the rule? What do we do with the exponents? Subtract them. Okay, now focus on this thing. It's no different, right? It's exactly the same pattern. So what do you do with the exponents? Subtract them. Okay, let's subtract them. It's a little bit more frightening because there's negatives involved, but it's the same rule. We still get to apply this subtraction property. So we subtract. So now we got to think about the order here. Which one gets subtracted first? Do we always do top minus bottom? Do we do bottom minus top? Do we do big minus small? Yeah, Chris. We could always do the top minus the bottom. We could also always do the bottom minus the top as long as we know what effect that has. So a real quick detour, I think this is worth pausing for. Suppose that we had x to the 5th over x squared. So doing top minus bottom gives us x to the 3rd. I'm just going to put a 1 here to highlight that that's upstairs. What if I had this thing upside down, x squared over x to the 5th? Let's just go ahead and subtract. Top minus bottom gives us negative 3. And again, I'll highlight that it's upstairs, right? So we could just always do top minus bottom. But the issue is that you might end up with a negative exponent, which is not so desirable. So we have to clean this one up. Where do we move the x to the negative 3? To the bottom. Then we get this. I'll put my placeholder there. So then here's a nifty shortcut that I apply and encourage you to apply as well. What can we do with the 5 and the 2 to get this guy from the beginning? Subtract the other way, right? You could just do 5 minus 2 and know that the answer is going to be in the bottom. How can you know the answer is going to be in the bottom? What about the 2 and the 5 tells you the answer is going to be bigger numbers in the bottom, right? I mean, like if you imagine all these x's written out, there's more of them in the bottom, so that's where they will end up. So this is what I do, and I suggest you do it too. I always do big minus small, and I put them wherever there were more x's, 5 in this case. Okay, so if we like this whole big minus small idea, then very carefully tell me which is the bigger number between negative 4 and negative 8. Negative 4 is the bigger number, right? It's less negative than negative 8. So let's do the big one minus the small one, so negative 4 minus negative 8. And where are we going to put the answer? Up on the top, because that's where there are more of them, even though it's negative. So we get c to the, very carefully, how much is negative 4 minus negative 8? That's positive 4. So we just get c to the 4. And then we'll reduce the 4 and the 8 just like we did before. 4 and 8 cancel to make a half, and we get that. Questions on that? and again, this is my recommendation, is to use the properties of exponents before we try to handle those negative exponents. Did we ever actually have to deal with the fact that they were negative exponents in this problem? We didn't, right? We didn't have to do any movement. We just did our property of exponents and all the negatives magically just disappeared. So I always encourage folks to do it in this order. But there are lots of different ways to do these, and it's okay as long as you get to the right answer at the end. Okay, and the last one I want to look at here is L. So let's look at L together. Okay, again, there are a couple of different ways to do this. I'm just going to do this one in one way, which is the way that I would do it myself. My property of exponent says I do what when I have an exponent outside of a product like this? Eleanor? It goes into everything. And I used the word distribute kind of loosely. It's not really the right word, but it looks like distributing, so we used it. So I'm going to bring that -2 and hit everything, as Ellie says. And so let's put our answer. So that means that the -2 comes in and hits the 2, like that. And it also hits this guy, so I think I still need parentheses like that. Does everybody see the -2 coming in to hit everything? Equals. Okay, 2 to the -2. There are a lot of tempting but wrong things to think. There's one right thing to think. What does 2 to the -2 mean? 1 over 2 to the +2. That's the only thing it means. So I'm just going to put my fraction, put the baby down, it becomes positive. 2 to the +2. It's really tempting to think that 2 to the -2 is -4. And I can just about guarantee at least one of you is going to put this on the next quest. 2 to the -2. Okay, we're just 2 squared is 4, negative at the end. -4. It's not right. Negative exponents have nothing to do with negative answers. Negative exponents mean move up or down. What do we do with exponents when they look like this? We multiply them. This was a different one of our laws of exponents, is that we multiply them when it looks like that. So we get x to the 6. And the nice thing, again, is that the negatives all disappeared, right? We had like a double negative, if that makes sense. It was x to the -3, but then it was raised to another -2. Well, that's a whole lot of motion to keep track of, and you can do it correctly. But much better is to just let these negatives cancel by multiplying them first. So our final answer, just cleaning up the bottom, x to the 6th over 4. Questions on that? Chris? So like make up a number to the -1. What does 5 to the -1 mean? 1 over 5 to what power? To the 1. So it means 1/5. And in fact, you have a button on your calculator that maybe you have never used before, but let's use it here. So if we say 5, and then do you guys see over here this x to the -1? Okay, so I'm going to hit that, and it's just going to put a -1. What is the answer going to be, given the calculators give decimals? 0.2. 1/5 is 0.2. So that x to the -1 button just says, flip it over. That's what negative exponents mean. Good question. Okay. Last thing we'll do, and then you guys have a lot of group work to work on today, is we're just going to speed through a couple of applications of negative exponents. Have you guys ever seen this acronym, BMI? Anybody know what it stands for? Body mass index, right? It's the body mass index. It's some kind of a measurement of a person's physical fitness. It's not the most accurate measure. It's a pretty rough estimate, but it involves a person's weight and their height. And you somehow multiply these two things together in exactly that way, and you get the BMI. And then there's like a chart where you look up, you know, like what the healthy range of BMIs is, and you hope you're in the healthy range. So why am I showing this to you? Well, what do you notice in the formula? A negative exponent. So here's an example of a formula which you may have, like you probably haven't seen the formula, but probably at your most recent physical, somebody did this calculation to come up with a number for your BMI, your body mass index, and it involves negative exponents. We're not going to look at the actual numbers here, but in any event, I just wanted to show that to you. And then one more example that involves negative exponents is scientific notation, which I think you've seen before. Let's take a quick look at two numbers. We're going to translate that massive number right there, which was the US debt about a year ago when I typed this thing up. And then we're going to look at this really teeny tiny close to zero number, which is the diameter of a bacterium, which is really small. And really big numbers and numbers really close to zero are kind of awkward to write, and they're also awkward to read. And so scientists who end up using these kinds of numbers often have invented this notation, scientific notation. And the idea is you're going to take the decimal point wherever it is, and you're going to move it. And you're going to move it in such a way that the number you end up with is between 1 and 10. So currently that first number is 15 trillion and change. If I move the decimal point over to here, just to the next spot, I'm not at 15 trillion, I'm now at 1,500,000,000,000, right? Like if we just move it over, and if we move it again, now we're just in the hundreds of billions. It's like 150 billion. And I keep moving until I end up with some number between 1 and 10. So where am I going to move that decimal point to ultimately to get something between 1 and 10? Between the 1 and the 5. This is the only place we can put it. If you put it here where this comma is, your number is 15 and change. I need it to be between 1 and 10. So 1.5 is the right spot. So we're just going to say 1.5, and then I'll round the next number up. And then we count how many times we had to move that decimal point. So very carefully from the starting place to the finishing place. How many spaces did that decimal point move? 13? So the national debt was about 1.55 times 10 to the 13, which is a lot easier to write and a lot easier to read as long as we understand what we're reading. And this whole times 10 shouldn't be so surprising, because if you multiply a number by 10, you just move the decimal point one place over, right? So all we're saying is that to get from where the current decimal point is to the real answer, you just got to keep moving that decimal point 13 times. And that gets you back here. Well, we rounded a little bit, so it almost gets you there. And it's the same idea for this bacterium example. Again, I got to move that decimal point so that I end up with a number between 1 and 10. Where can I move it? To just after the 2, right? Because now the answer is, I'll put a little 0 there at the end. Now the answer is 2.0, which is between 1 and 10. So this guy in scientific notation, you don't need the 0.0, but I'll put it. How many times did that decimal point move? It went 7, but it went the other way. That's negative. And the reason that negative makes sense is because 10 to the negative 7 really means what? Yeah, like just this guy means 1 over 10 to the 7th, right? That's our definition of a negative exponent. And we know that dividing by 10 just moves the decimal point the other way. Right? Multiplying by 10 moves it to the right, dividing by 10 moves it to the left. Okay, I'm not a fan of saying, if you move the decimal point to the left, then you put a positive exponent, and if you move it to the right, you put a negative exponent, because half the time you'll get that wrong. But I am a fan of saying, you guys know that 10 to the 13 is a very big number. So if my choices are 10 to the 13 or 10 to the negative 13, and I want a big number, okay, it's got to be positive. What you have less experience with, but maybe you're going to start to gain some experience, is that 10 to the negative 7 is really like 1 over 10 million, which is very close to what number? 1 over 10 million is very close to what nice number? 0, right? It's just a hair's breadth away from being 0, 1 over 10 million. So if you have a number very close to 0, you'll start to get this intuition that you got to have negative exponents. So I'll just write this one thing here. Big number leads to positive exponent. Little number leads to a negative, and by little I mean close to 0. Okay, so 40 minutes to get through the group work today, and there's probably about 40 minutes of group work. So let me show you where we're starting. On the very next page, there's a table you're going to fill in. Don't do it just yet. The page after that, an introduction to square roots, but I think most, if not all of you, have seen this before, so this should be pretty straightforward to just read and then work on the problems. But before you do that, I want you to go back to that chart that we filled in a couple of. Starts at number 4 on the top. Everybody see the chart? Starts with number 4. What page is this? 10. So start on page 10, fill in the rest of the chart with your neighbors, then jump to the 2 different group activities. Okay? Yes. Okay, so I'll come around, I'll check homework for people that came in late. Again, tests can go into the folder, and let's see how far we can get.